The robot controller designed an HTML GUI design for controlling the robot. This is the forward button. It allows the robot to go forward, and then the left and the right, which allows it to turn, and the back so it can reverse, and then stop so the robot is able to stop.
Alright, so this is just one of the labs I did for the sensors. Basically, we have a infrared sensor, and it basically when it's triggered, the light will emit. It's originally low, and then when the sensor is triggered, it'll be high, and the light will emit.
All right, so this is our Raspberry Pi controlled robot called Paloma. There's a motor shield on top of the Raspberry Pi stacked onto the GPIO with a header. The motor controller supplies the motor blocks through which the DC motors are driven. As you can see, it's taking 9 volts to supply power to the DC motors. And I've got it set up to run 2 ways. We can execute a script from the Raspberry Pi itself. Have some power issues. Give it a little push. And the wheels start to rotate forward. And then subsequently, I can execute a stop script.
Well, you can demo ones that there's a two, but keep in mind.
And that kills the motors. So that's the first level of control, is from the Raspberry Pi itself. We are also using the Raspberry Pi as a web server to host a simple HTML website. This is what it looks like. Unfortunately, we ran into an issue where once the script is executed, the process will not die. So once I run the forward script, I can't stop it. But we're going to give it a shot anyway. So this is the button we're using to start it, the light on. And again, give it a little push. You can see the motor start. And unfortunately, at this point, we have to reboot the Raspberry Pi because I cannot figure out how to get this process to start. So I'm going to shut it down and then remove power. And that's about it.
Our project is Paloma by Shifali Mengi, Michael Gomez, Maya Hill, and Lizzeth Valencia. Our goal is to have a small robot controlled by a microcontroller, which will be controlled from a touchscreen display known as the Raspberry Pi, native GUI written in Python for control over Bluetooth, and a web page designed to drive the robot over any web client. Include a camera to display video on the Raspberry Pi and on the web client. We divided the work among our group. So Maya's task is to create a sensor interface from RPI to website. Liz's task is to implement a camera using the Raspberry Pi. My task was to create an HTML button and GUI design, also create a webcam using HTML. Michael's task is to manage the project and develop the server. The task that I created was I created an HTML GUI design in order to control the robot. So the forward button is moving forward, left and right is for the turns, back is to reverse, and stop is to stop the robot.
Okay, and this is the bill of materials, or the list of materials that we use to construct the robot. So we use a Raspberry Pi 3B+. We used an Adafruit Raspberry Pi motor hat, which is a shield that sits directly on top of the Raspberry Pi. It stacks onto the GPIO pins for control. We purchased a 4-wheel drive robot chassis kit with 4 DC motors to drive the robot. Used a 9-volt battery to power the motor hat. Flying fish IR sensors to develop our sensor interface, and a breadboard for prototyping. And this is a photo of our robot. So So the final outcome, we were able to achieve control of the robot using the website, which was actually hosted on the Raspberry Pi, using the Raspberry Pi as a server. The server framework we used was LightTTPD, which is a fast and lightweight server with a small memory footprint, perfect for the Pi's limited processing capabilities. For the purposes of the lab, only clients connected to the local network had access to the website using the IP address of the Raspberry Pi. The HTML page was written to execute CGI scripts, also hosted on the Pi server. The CGI extension stands for Common Gateway Interface, a common method for clients to access resources that are hosted on the server. In turn, the CGI scripts were actually Python scripts that use the Adafruit motor library to control the robot itself. So to simplify, the buttons that were located on the controls website actually went and fetched these CGI scripts for execution.
And a few of our challenges that we had were basically that giving proper file permissions to the Raspberry Pi and the client to control the robot. This involved debugging, use browser developer tools, and discovering the www-data user needed to be added to the I2C permissions group. In addition, when each CGI script was executed, the process would not die, and when the next script was executed, the logic issue could that can be fixed, but that could be fixed in the code. So basically, our robot would continue to run once it was executed, and we couldn't terminate the code. Another significant obstacle that we encountered was when we realized that the motor hat occupied all the GPIO pins on the Raspberry Pi. Therefore, we couldn't include the sensor-driven auto mode, and perhaps including another microcontroller and using serial communication. This feature could have been incorporated fully. And lastly, one of our challenges was it was very difficult to include the camera with our Raspberry Pi. It was just a matter of more investigation and time. Our future goals were to incorporate some kind of machine vision algorithm using the camera for self-driving, incorporate the self-driven automatic mode, and fix the website so that the scripts interrupt each other. Include a module that displays the camera input on the controls website, and eventually develop the website to Heroku or another service to make it accessible by domain name.